Hello, my name is Ivan. Welcome to the module Simulation Robotic Systems. And in this video, I will give you detailed explanation for the practice tasks. So let's dive into the presentation. All right, so the first task is about first experience in MATLAB. How can you do multi-body simulation? And we will use PID control to actuate a closed chain linkages. So I believe it is the simplest system that can be considered if we think about multi-body systems. So first of all, I will give you some motivation. Why do actually we need it? Then we will proceed to some definitions. Then I will show you how can you make your first steps. So I will give you a live demo. Then I will show you the elaborated examples that you will be provided. Also, I will give you some intuition about PID control, and we will wrap this up with the variants of your practice tasks, and we will finish with the conclusion. All right, so mechanisms, there are a lot of different kind of mechanisms. They consist of different subsystems such as gear strains, counts, cables, springs, a lot of stuff there. But linkages are the most challenging to design, to develop, and it is crucial. And if you consider any robotic system, you will find linkages there. Every robotic system contains linkages. All right. So some definitions, such as you can understand fully what I'm talking about. So link, I believe that you know all this stuff, but nevertheless, link is the individual body, and the robot consists links. Links are connected to each other by means of joints. There's a lot of different kind of joints. There's, I believe, dozens of joints. But the most popular, the most common is a prismatic joint that allows one body to move linearly in respect to another, and a revolute joint that allows rotation of one body in respect to another body. If we consider an assemblage of links that connected by joints, we call it as a kinematic chain. The mechanism is a kinematic chain with a fixed link. And there's a different kind of mechanism. Within this practice, we consider closed chain. It is the one where you can find a link. It's like all the links contains at least two joints. An open kinematic chain is the one where at least there is one link with just a single joint. There's parallel chains, also important concept is the configuration variables that basically allows you to use those numbers, those variables to describe the whole configuration of your system. And degrees of freedom, it's the number of those configuration variables, basically. All right, so now we will consider the simplest closed kinematic mechanism, closed chain mechanism. This one is called 4-bar mechanism. So here, basically, you can see only three of them. Because only three are able to move, and the final one, the fourth, is fixed to the ground. And here we can see different types. I mean that the structure is the same, but the length are different. And here you can see the important feature is such that you can have the same structure, but if you have different parameters, you will get different trajectories, right? And here you can see only revolute joints, but also you can use not the revolute joints, but the prismatic joint. And the simplest closed chain mechanism with the prismatic joint is a crank slider mechanism, as you can see here. So, for example, this kind of linkage is used for the internal combustion engine. All right. So we will consider those examples as examples. All right. So let's now have a little demo. Here, it is the MATLAB, the program that we are going to use in our course. And the first thing that you need to do here is to write down the command smnew. It is the command to open Simulink, but not just Simulink. If you will write down this command simulation model new, you will already have the initial blocks that are needed, such as the world frame, the solver, the block which is called mechanism configuration, where you can adjust the gravitation. I mean, you can write down basically along what axis your gravity is applied, and some extra blocks. So let us consider this. So this this window is the Simulink, and here those blocks, those are blocks of Simscape. So here we have some links, and we can start with it, just dive in this library, to this library. So here we can see the Simscape. It is like an additional block inside MATLAB, inside Simulink. And here we can model whatever you like, for example, gears, some electrical components, fluid components, a lot of stuff here. But within this first practice, we will consider multi-body dynamics. So here you can see different kind of joints. So there's a lot of them. There's belts, cables, gears, some kind of transformers. So there is a lot of stuff here. And take your time to consider all the components. So I will not give you a detailed description for all of these parts. My task here is just to give you the first step. All right, so here we can see several blocks, what it is. First of all, it is solver. Is the one that allows you to solve differential equations. So we don't need to change here anything. It is the world frame. It's the frame which is fixed to the ground, to the space. And the last one is the one where you can write down the coefficient of gravity. So here you can see that X, Y, and Z, that you have a number for the Z component. It tells us that the gravity is applied along the Z axis in negative direction. Whereas if you just run it, you will be able to see only this world frame. So you can see it. So the only world frame exists in our system. If we add this brick solid to the world frame and run it, you will be able to see the object which is connected to world frame. So inside this block, there is a lot of parts, a lot of going on here. Also, take your time to consider all this. I will just give you the essential stuff. So here you can change the dimensions. You can change units. For example, now it will be 10 centimeters long. and in cross section it will be 1 by 1. Here you can describe inertia. Now it's based on that density, and if you click update, you will see what is the mass. I can increase density for 8,000. It is steel. If I click update, you will see that now mass is bigger. I can say that it's based not on the density but mass, and leave it like this, and it will calculate the density. I guess it's plutonium, so it's not something maybe that exists. I will leave with 8,000. It's something that makes sense. All right, if I click apply, you will be able to see this object. So let me change the background on the white color, such as it will be more pleasant to see. All right, so here you can see that we attached the body in the middle, right? It is the frame that you can see, because initially every brick, every body have a frame which is in the center of the body. Let us consider that we want to connect this brick in different place. So let me create another frame. So here I need to choose frames, press on this little plus icon and change where do I want a new frame. So I want frame here. I click based on geometry feature here at the origin and press use selector feature. And then I press save, apply, okay. Now you can see that there is extra F1. And now if I will run it, you can see now that the world frame now here. So we changed the way how we connected this body. All right. So I will get rid of this R because I do not need it. Now you cannot see. And let me call it as a link 1. And let's get some motion. So you can find the revolute joint from here and just to move it like this, or you can just type the name here. Revolute joint, yeah, like this. So you have two options. All right, we put it here. You press 1, and nothing happened. Why? Because the z-axis, the revolute joint works only z-axis. And if you consider your system, your z-axis is vertical, so there is no force which is applied to the system. If we want to get some motion because of gravity, we need to rotate the whole scene on 90 degrees along the x-axis, the red one. All right, so let's rotate it. To rotate the whole scene, we need this rigid transform block. So we need to rotate on the x-axis on 90 degrees. Press apply. And now you can see that the whole scene was rotated on 90 degrees. And now our body is able to rotate because of the gravity. All right. But since all right, so what do we here? So there is a lot of stuff going on here. For example, you can adjust initial state. You can do actuation here. You can do sensing, but also we can write down here some damping, for example. And yeah, it's a lot, since we have a very a light object. Yeah, now it's okay. So it's like if it's close to the physics there's friction. Before there was no friction, and because we do not have any friction, we do not have any energy loss. We had oscillatory motion without without energy loss. All right, what else can we consider here? Before we just created only one frame. Now let us consider to create another frame. For example, here, also I press based on general feature, use selector feature, save, apply, OK. Now we have two of them. We can copy this stuff, place it here, connect it, B, and run it once again, and we will have a double pendulum. We can create a triple pendulum, and we can do whatever we want. All right, let us consider what can we do with the motion. So here we can say basically that the motion is provided by input and torque is computed. Let us consider a simple way. So now you can see that there is a little icon, and let us suppose that we want to have some sinusoid, okay, let's have a sinus wave. Sinus wave, yeah. But we cannot connect it directly. We need to use a transformer, because this one is just number, but we need to give a physical, not a signal, but something physical. And because of that, we need to write down here the units, and also we need filtering, because it's not going to work without it. Because even if your signal is smooth, the MATLAB consider that it's not smooth enough, and it's not able to derive derivation, and you will get a error message, as you can see here. If I will just send it right here, you will have a error that it's not able to do derivatives. And this is why we need to use here filtering. And now it works, and you can see that this one works. And since we chose here that the motion is provided by input and torque is computed, we can do sensing to get the torque, which one was computed. And here in the scope, you will be able to see torque. Yeah, it is the torque that was computed. All right, but I call it as cheating, because actually you need to do your own controller. So another version, another option is to use the torque is provided by input and motion is computed. And we will use now a feedback PID control. And for the feedback PID control, we need feedback, right? So I will click that we need to sense position. All right. Before I proceed to the PID, I need to go back to the presentation. So about the control, if you feel that you do have some gaps in your knowledge, I recommend you this nice book of Kevin Lynch and Frank Park, which is called Modern Robotics. And here you can consider reading whatever you like regarding the stuff that I'm talking about. For example, robot control. So here you can consider everything from the beginning. You can consider the aerodynamics, PID control, all this stuff from the initial beginnings. In my presentation, I just want to give a brief introduction on this stuff. Everything that I'm going to say right now is based on this book. All right, so basically when we talk about the control, there's a lot of stuff going on. So there is a desired behavior that we send to the controller. Controller takes into account the data from the sensors. Then the controller computes the low power controls. Then we have amplifiers that increase the power of control. It sends it to the actuators. Then actuators send all the efforts, such as force torques, to our plant, the robot. And then the feedback, we use feedback to get the state of the robot. And okay, I believe that the concept is clear. But within our first simulation models, we will consider a simpler model. We will consider that our controller computes all the forces and torque which is needed to move the robot. All right. Okay, so the PID works as the mass spring and damper system. It's all about the difference between the desired position and the actual position. And we can consider about this error position as the spring deflection. If we multiply spring deflection on coefficient of stiffness, we will get the force which is generated in the spring. If we take here a mistake, let me fix it very quickly. If we consider damping, if we want to compute the force which is generated in this damper, we need to multiply coefficient of damping on the velocity. So here, and you can consider this one as the PD control, as the PD controller. And you can consider reading the Kevin Lynch book about E-component. So this is how PID controller looks like. So we have our robot, we use controller to get the state of the position. We compare the actual position with the desired one, and we compute this error. I say position because it's related to the example that we consider, but it can be actually anything. It can be velocity, it can be acceleration, it can be force, it can be a level of fluid in some bucket, I don't know. So it can be anything actually. All right. This is the equation. So if we want to compute torque, which is needed to be applied to the robot, we need to take this coefficient, proportional coefficient, multiply with the ER. Then we need to take a proportional I component, multiply with the integral of the ER, and the last one is the D component coefficient, multiply with the derivative of the ER, and we will get the torque which is need to be applied. All right. So I think this one is pretty obvious. If it's not obvious for you, please consider reading the chapter about the control in modern robotics book. And here you can see the effect of changing the coefficients. So first of all, here we can see how we can increase a P component, then E component, and to kill all the oscillation, we increase D component, right? So from here you can feel, you can get the intuition, you can get the feeling about what is the purpose of each coefficient, right? Because we will going to need those coefficients to control our robot right now. All right, so let us go back to the MATLAB. So as we discussed for this our PID, as the input to our PID, we need the difference between the desired behavior. Let's just consider that we want to get the same motion for the second component, and we need the current state. So here we need to write down radians. By the way, here we need to write down the unit, such as we confident in what we are doing. All right, and the last part is to connect here. Yeah, torques is measured in Newton per meters, and here we do not need filtering because all filtering is already done in this controller. Right. So, and now we can play with the coefficients. I will just something arbitrary that I believe is going to work. Yeah, it's something something feasible. All right. The last stuff that I would like to show you is how to consider how to take a look at the signals without using scope. For example, here I will write down this. It is actual position. This one is desired. This is here. It is a tau. And now we can press here on this little Wi-Fi signal. Let me do this for all of the signals. Right. And press 1. And now you will see this data inspector start to glow. And if we press it, you will get this window. And here you can see everything that you chose. For example, this is tau, and this is our angles, right? Okay, so this is everything that I would like to show you regarding a quick demo. Now let us consider the elaborated examples. So I will save it, such as if you want to take another look. All right, so here, let me close. All right. By the way, here you can see that the workspace is not clear. To clear it, I use command clear, and to clean everything in this command window, I use CLC. All right. So I will send you the elaborated example here. The first one that I developed is the for-bar mechanism, and to run it, you need to open this live script. So here you can see a lot of stuff. and you can just press run and it will open it up and everything is going to work. All right. Yeah. I haven't done it here. All right. Let me. Okay, we can do this. Differently. So we will run parameters. We'll just change the yeah, now it's focused. Yeah, it was there was a problem in the order. All right, so here we can see. Okay, let me just check it once again. So I will clear everything and run it once again. Does it work now? Yeah, it works. Okay. So here we can see a 4-bar mechanism, the one that I mentioned in the slide. Make some changes here. Yeah, now it's okay. So, all right. Here you can see the model that I have created. So it's pretty much the same that we done right now, but now it is a closed kinematic chain with all the joints that need to be done with all the links. And here you can see that it's not just bricks. It is a nice, it has nice shape, and there is no penetration of one object inside another. So it's nice animation. So consider this model with your pace. So there's nothing strange going on here. So there's a PID. So everything is fine. Something that can be new for you is a sensor. So this sensor can be used to measure whatever you want, angular velocity, linear velocity, translation, everything that regarding kinematics. All right. What else? Maybe those can be new for you. It is just a go-to from block. You can consider it's just like a Wi-Fi signal without any ropes, so you can just delete it and connect it like this, and it will be the same. Yeah. Troubles with that. Yeah. So it's basically the same, but to have clean workspace, I use this go-to blocks. So there's a switch. I think everything is pretty obvious now. All right, so here we can try different kind of inputs. For example, constant signal, like a step. Then ramp signal, continuous rotation. And sinus. So yeah, it works. What else? I think if you do have any question, just let me know in the chat in the Telegram. Another example that you will be provided is the crank slider mechanism. And did I change it? I guess I didn't change anything here. Yeah, before I proceeded to the crank slider mechanism, I would like to tell you about this live script. So here you can see the live script, which is needed for your report. So here you can see the example of the report. So here is the title. Here you need to write down your name, and another title. Here you need to write down what was your task, problem statement, then the parameters, then some script to run the model, and then some script to create plots. If it's not familiar to you, you can always use documentation. Just press F1, and you will be able to read everything regarding the script. So here you can always find everything, but I believe it's pretty obvious. All right, so here you can see a plot of some point F, right? Yeah, it is a trajectory. Then this is the angular position of the input link, the one which is connected to the actuator. There is the desired, actual, and the error position. The coefficients are not optimal, and this is why error is not equal to 0. And this is the tau, and here you need to write down your conclusion with the reflection. Let me show you the second example. The crank slider mechanism. It's pretty much the same, but with the prismatic joint here. Here, the challenge is to find out how can you attach prismatic joint. So for the revolute joint, the z-axis, the blue one, always look at you. But for the prismatic joint, it needs to be orientated along the motion. So prismatic joint also orientated also works along the z-axis as a revolute joint, and due to this fact you need to consider frames. So here you can see that the frames are orientated differently, and to change the direction of frame you can use a rigid transform block here, this one, to rotate it, or you can just use those tools to change the direction. All right, let me continue with the slides. So here you can see the problems. There's three variants. So those you can consider those, maybe it is complex, but it's not really complex, because here you can see that it is a 4-bar linkage, EABC, with just extra stuff. And here you can see some hints. How can you assemble this one? Another kind of mechanism, and here also another one. So your task here is to understand which one is the input one. But here you actually can use both of them, which is connected to the frame. For example, this one obviously is not able to do the full rotation, and it's not good enough for the ramp. Here also the link HF is not good enough for the crankside, since it's not able to do the full rotation. So I believe that EA only the one. Here also it's pretty obvious that DAC is the input one. All right, so those are the problems. And let me now open the variants. So here you can see the list with your ISO numbers, and here you can see the data for your variance. So I use a random numbers. For example, if I will write here something, you will see that everything is changed. So I use it to create random examples for such as everyone get a personal variant, an individual one. So here, for example, if your number is this one, you need to take the third linkage. You need to consider density. So here is the density that you need to use for all the links. This is the parameter A. It is this one. Here you can see that AB equals to CB, MB equals to A, right? And this the same here and the same here. So there's our A. And also, and the last table is the input source that you can see here. So if your number is 1, you need to use a sinus wave to ramp. And if you get 5, you can use anything you like. All right. So here I save it as a PDF file. All right. So I save it as a PDF file, such as now it fixed to the ground your data, and it's not going to be changed now. All right, what else? So this is the problems, this is the source type, and in the report, you need to write down the problem statement. What is your task? What do you want to get? What do you want to get? You need to get useful data. You need to study these linkages. So what can it be? It can be trajectories. It can be velocities, forces, accelerations. So any kinematic or force data. Everything that you can use to get some reflections. So our task not just to create thousands of plots without any consideration of what we have done. Do some plots such as you can reflect on it and give some comments about the data that you see, right? So you do the problem statement. You, for example, you write down. All right. So, for example, this HF is obviously a rocker, is not a crank. It's not able to do full rotation. You can do a plot of angular displacement and show it. Yes, it's not. It's obviously is not a crank. It's able to do only 30 degrees motion, right? What else? So you need to write down all the relevant equations. For example, here is the equation of PID control, any necessary description. You need to do plots and you need to reflect on your data. All right, so to wrap this up, here in this video, I give you some little intro about the linkages, about the PID control. I gave you a little demo for the Simscape, and I believe that I give you a detailed explanation for the practice 1 task and everything that need to be written down in the report. Thank you for your attention. If you didn't get it, you can always write a question in the chat. That's it for the first task.